So in this screencast, we're going to start our third phase on chemical reactions and properties and such. And so now we start the long, hard slog of using chemical equations. So we spend a little bit of time sort of like talking about equations and what they are when we balance them and why we balance them. First, I want to take a moment just to plant in your head a comparison set of information. Here is a, not real, but pretend it is, recipe for making cookies. And here are all the ingredients, and if you mix all these ingredients together, you get 48 cookies. This is what I'm going to refer to as simply a recipe card. And what it does is it tells me the ratio of all these individual ingredients and how much of each thing I need in relationship to how much thing I need. This recipe card can be doubled, it can be cut in half, it can be multiplied by 10. And if that was the case, I would simply multiply each one of those individual amounts by 10, and the number of cookies that I would get would also be multiplied by 10. A balanced chemical equation, at the end of the day, is nothing more than a recipe card. Balanced chemical equation tells you what you're making in the kitchen that day. It doesn't say anything about how much you actually make, because the amount of your reagents might change. All a balanced chemical equation is a recipe card. Keep that in the back of your mind, and it'll make life a lot easier. So chemical reactions, when we write them, they're reactants sort of going to products. So here is a chemical reaction where I have wheels plus frames goes to bicycles, and I can tell because I know that bicycle, that somebody told me that a bicycle has 2 wheels and 1 frame, so this is not a balanced chemical equation. Now, you might have learned that when you look at a chemical equation or chemical reaction, if there's no numbers in front, you just sort of assume that everything's a 1. Well, at this stage of the game, that's sort of bad karma, because when you come upon an unbalanced chemical reaction, by definition, if it's unbalanced, there's nothing in front of anything, so you might think that it is balanced and that everything's a 1. And in this case, it's not. So it's always better karma that even if all the numbers are 1s, to actually write the number 1 in front of them. So when I balance this chemical reaction, this is a balanced chemical reaction. And when I'm grading your quizzes, there has to be a 1 there. And it'll make life a lot easier for you. It'll totally cut down on your mistakes if you just put the 1 when you know it's a 1. Just trust me on that. So now I have my balanced chemical equation. And again, this is just a recipe card. For every 1 bicycle, I need 2 wheels and 1 frame. Now I can double the recipe, and that's totally cool. I just have to multiply all those numbers by the same number. So I can make that a 4, that a 2, and that a 2, and it's still a balanced chemical equation, or a balanced equation. I know if I take 4 wheels and 2 frames, I get 2 bicycles. Still balanced. So again, this is now a balanced chemical equation, and it's just our recipe card, and it tells us our ratio. We have the same number of wheels on both sides of the reaction, and we have the same number of frames. If I have 1 bicycle over here, I have 2 wheels and 1 frame, and I started with 2 wheels and 1 frame. So I have the same number of each element on both sides. Now, when we write our chemical equations, we also put sort of subscripts behind them to indicate their physical states. And there are 3 main physical states that we talk about. There's solids, liquids, and gases. Solids are given the symbol S, gases are given the symbol G, and liquids are given the symbol L. And then there's this 4th one that you're going to see often, which is AQ, which stands for aqueous, which by definition means dissolved in water. That's the definition of aqueous. So whenever you see this NaCl parentheses AQ, that means aqueous, or just dissolved in water. And in general, if you know the states of the particular substances in question, you generally add them to the equation. The reason that is because, for example, water liquid behaves differently than water gas. So if you know what they are, you tend to put them in. So here is an example chemical reaction. It's the reaction between hydrogen and oxygen going to water. Now we can probably balance this one relatively easy just by inspection. We know that we have 2 oxygens sort of on the left-hand side and only 1 oxygen on the right-hand side, sort of as written. So for every 1 of these oxygen molecules over here, I can make 2 of these water molecules over there. And if I put a 1 there, that means I have 2 oxygens here, and I put 2 oxygens over there, and now I have a total of 4 hydrogens, so I'd put 2 hydrogens over there. And so now I have 4 hydrogens on the left, 4 hydrogens on the right, 2 oxygens on the left, 2 oxygens on the right, so the reaction is balanced. Now we are going to find out, this is sort of like by inspection, because it's relatively straightforward. We're going to have sort of a system to this. But the key is that the number of each atom has to be the same on both sides. And again, there's more than one possible answer. In fact, there's an infinite number of correct answers. So we could put a 4, a 2, and a 4, and we'd still have the same number of each element on both sides. And again, this balanced chemical equation says for every 1 mole of oxygen that reacts, there are 2 moles of water produced. And the key here is I say mole of oxygen, mole of water, because these are actual number of molecules. For every 2 hydrogen molecules, I need 1 oxygen molecule, and I form 2 water molecules. It's sort of like the base what this says. But remember, when we're doing actual real chemical reactions, we're not going to be dealing with individual numbers of molecules because that's just too small. We're going to be dealing with large, buckets of water and beakers full of water. And if we talk about the individual number of molecules, that's just unreasonable. So the concept that we use to talk about large numbers of molecules is moles. So this does not say 2 grams of hydrogen, 1 gram of oxygen gives me 2 grams of water. Very, very clear. This is actual number of molecules, but when we talk about number of molecules, we're talking about moles. So that's what this reaction says. For every 1 mole of oxygen that reacts, I get 2 moles of water. It also says for every 2 moles of hydrogen that react, I get 2 moles of water. It's just the relationship between all of those ingredients and the number of all those ingredients and our products. And we can interchange. They're all related by this sort of ratio 2 to 1 to 2. So we can compare any 2 of them that we want, whatever we want to. Here's a reaction between nitrogen and hydrogen to form ammonia, a chemical reaction of historical significance. And there's 1 nitrogen for 3 hydrogens, and I have an N2. Now, what you might be tempted to do is put a 1/2 here, because there's a 2 there, so you put 1 nitrogen on the left-hand side and then put a 1 there. Is that legitimate? Yes. Is it common? No. Generally, we have whole numbers as our stoichiometric coefficients. That's those numbers in front. You can have fractions, and there'll be a couple cases later that we'll talk about where we have to do fractions and we don't have a choice, but generally not. So if we make that our 1, because we want small whole number ratios, then we'd have to have 2 nitrogens. That would give us 6 hydrogens on the right. So to balance out our hydrogens, we need 6 hydrogens on the left. All right, so those were 2 real simple, again, sort of by inspection, ways of balancing chemical equations. There are a couple of, there's more than one way to skin this particular cat. I'm going to give you one sort of generic method for balancing chemical reactions and give you an example. And there's lots of stuff. If you learned a different way in high school or some other chemistry class that you took, that's fine. This is not exactly a really difficult concept for most college students to pick up. So if an element occurs only once on each side of a chemical equation, we generally balance that one first. And then our other strategy is the free reactants, where there's 1 element, we balance those last. And this will make a little bit more sense if we talk sort of about using our example, because we can see both of these sort of strategies in this first example. So here I have the combustion of ethanol in the presence of oxygen to form carbon dioxide and water. So let's take the last part first. So it says balance the free reactants 1 element last. So we're actually going to end with this oxygen. And the reason we're going to do that is when I put a number here, and that's how we're going to do this, is we're just going to go piecemeal and do 1 at a time, put numbers in front of each one of these components. When I put a number in front of the ethanol, the idea is that once you put a number there, you don't change it, unless you know you made a mistake. So when I put a number here, it sort of locks down the hydrogens and the oxygens and the hydrogens in this molecule. So as we put numbers in front of these, we're sort of balancing them 1 element at a time. So we want to leave oxygen to the end because it's a free reactant. We kind of want to leave it to the end because when I put a number here, it doesn't affect any other element. The first one, it says if an element occurs only once on each side, balance that first. Again, we're trying to balance the individual components, and we see there's an oxygen there, an oxygen there, an oxygen there, an oxygen there. So trying to balance the oxygen first would be a colossal pain. Now, what I mean by only once on each side, so hydrogen is only in this molecule and in this molecule, so we can balance that first, but I'm actually going to choose to balance the carbon first because it's only here and there. So as it's written, there's sort of an assumed 1 here and nothing there, so to balance the carbons, if I put the 1 there to sort of lock it down, then I have to put a 2 from the carbon dioxide. So now the carbons are balanced. So then, since we know we're going to leave the oxygen last, we should balance the hydrogens next. So I look over here, and since I put that 1 there, which is really important, I mean, if you want to get it right, then it's really important. Then I have 6 hydrogens on the left-hand side, and as written, I've only got 2, so the number that I have to put here to make all the hydrogens balance is a 3. Now I have 6 hydrogens. And now I'm only left with the oxygens, the only species that doesn't have a number in front of it. And so I look on the right-hand side, because everything's locked down on the right-hand side, so I have 2 times 2, so I have 4 oxygens here, and then I have 3 more oxygens over here, so it's a total of 7. And we're trying to figure out what number to put here. We know we have 1 oxygen here, and it's sort of locked down with that 1, so it takes one of them, so we only have 6 left. So I have to come up with 6 oxygens here, so which means I make that a 3. And of course you can always go back and double check to make sure that your equation's balanced, just to make sure that you've got the same number of everybody. You can go back and recheck 2 carbons, 6 hydrogens, 7 oxygens. In practice though, if you follow the rules and put that 1 in there and sort of lock it down, you never have to go back and double check because you've already consciously gone through and balanced each one of those individual elements. And the only way you're going to screw that up is if after you put a number there, you change it. Or in the beginning, if you were to, when instead of balancing it, put a 2 there and leave this blank, if that 1 wasn't there, then you might be tempted to later when you're balancing the oxygens to do something over here or do something different with the hydrogens. Just cause confusion and make mistakes. So again, we just for sort of semantics, we will call these stoichiometric factors. So this 1 to 3 to 2 to 3 is the stoichiometric factor, or another way of thinking about it is it's the ratio of all these elements. So for every 3 moles of oxygen, I need 1 mole of ethanol, if I'm following this, and for every 1 mole of ethanol that reacts, 2 moles of carbon dioxide are produced, assuming I have enough hydrogen. So this the term that we're going to use when we're doing equations with these numbers is called stoichiometry, and this is where the term comes from, because these are stoichiometric factors. And now you should open up your problem set and do a whole bunch of chemical reaction balancing. Just make sure you're cool and hip with it.